Okay. Um, Welcome everyone to the DDPS seminar today. Before we introduce our invited speakers, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor to host Professor Weinan Yi, who is a professor in the School of Mathematical Science at Peking University and a professor in the Department of Mathematics and program in Applied and Computational Mathematics at Princeton University. His main research interest is numerical algorithms, machine learning, and multiscale modeling with applications to chemistry, material sciences, and fluid mechanics. In recent years, he has also developed an interest in control theory and related fields. Weinan was awarded the ICIAM Coolidge Prize in 2003 and many other numerous the awards. And today, Weinan will give a talk about machine learning and multiscale modeling. Please expect a wonderful talk and enjoy it. Now, without further ado, let me pass the baton to Professor Weinan by asking our usual question. That is, what is your favorite things to do other than research?
One of my favorite things other than research, I cannot think of many. I could actually maybe staying with the family or something like that.
Staying with the family. Oh, so you're like almost 100% focusing on your research, I guess.
Well, other than research, I don't know what else to do.
Yeah, okay.
Stay with the
All right.
family.
Yeah, yeah. All right, sounds good. Stage is yours.
It's an unexpected question. Anyway.
Okay,
Okay.
it's yours. Yeah.
Yeah. Thank you very much, Yansu, for the invitation and for the introduction. So I'll focus on something which really I worked on for very many years, namely multiscale modeling. And honestly, I wrote this book. I wrote this book 2011, Principles of Multiscale Modeling, perhaps one of the hardest books to read. Because at the time, 10 years ago, because I felt that, this paradigm of multiscale modeling, even though it's extremely attractive, I felt at the time that really wasn't going anywhere. Really, we were really hitting the walls. And I thought I'd just wrap up what I understood about the subject and turn on something else. And the something else I decided to turn on to was machine learning. And to my surprise, machine learning seemed to be the missing tool that we didn't have in multi-scale modeling, and it certainly changed my perspective on multi-scale modeling. So that's what I'm focused on: machine learning-based multi-scale modeling. And the key question is how we can construct interpretable and truly reliable physical models using concurrent machine learning. So let me explain this. We really want new physical models. It's not just an algorithm, but we really want new physical models, just like fluid mechanics equations, like new Navier-Stokes type of equations. And in order to have that, for that purpose, we really want the model to be interpretable. That's one requirement for being a physical model, and truly reliable. So that's one thing I need to stress. Nowadays, it's fairly easy to run some simulation, get some data, and using PyTorch or TensorFlow to come up with a machine learning model, neural network model that fit the data very well. So that's fairly easy to do. That doesn't mean we have a truly reliable physical model, and there's a very big difference in the two. So that's one thing I want to stress. The second thing I want to stress is concurrent machine learning, as I was explained in more detail below. Usual machine learning that people are doing in AI in our language, in the language of multiscale modeling, would be called sequential, because somebody produced the data beforehand, and then somebody else does the machine learning to fit the data. So that's a sequential mode. And the kind of machine learning we will face are concurrent. If you know about, if you heard about these terminologies in multiscale modeling, there was sequential multiscale modeling and concurrent multiscale modeling. So the multiscale, the machine learning we're doing is also concurrent in the sense that you generate the data on the fly as you train the machine learning model. So I'm going to explain these things more in detail. But let me mention my collaborators, Roberto Carr in Princeton, Jitun Han in Flatiron, and Huan Lei in Michigan State University, and Han Wan and Ling Feng are both in Beijing. Okay, let me start with this multiscale modeling paradigm. We have a hierarchy of physical models down from Schrödinger equation, quantum mechanics, to density functional theory, classical molecular dynamics, coarse-grained molecular dynamics. That's often used in, say, chemical engineering or biomolecular modeling, and Boltzmann equations, continuum mechanics like in fluids or solids, elasticity, and turbulence models. So this is perhaps a comprehensive list of all the most basic physical models that we use in different subjects of science and engineering. Now, the difficulties with these models is that other than the Schrödinger equation, all these other models requires some modeling component, by which I mean, for example, well, let's come here. For example, the constitutive equations in continuum mechanics and the potential energy function in molecular dynamics, or the density or the exchange correlation functional in density functional theory. These are part of the model that we need to come up with. So in the old days, how do we come up with the models? So for example, for this has been a huge problem. For example, in non-Newtonian fluids, we need to come up with these constitutive equations, and there's lots of proposals like generalized Newtonian model, Maxwell models, co-rotational, co-deformational models, and they're all ad hoc in a way. So the problem with these models is that they're not very reliable. And then the same story is also happening in other situations. For example, in turbulence, it's well known that we need to come up with these ad hoc heuristic turbulence models like K-epsilon models in RANs. And in density functional theory, there's different proposals about how to model exchange correlation functional, and et cetera, et cetera. So in the absence of systematic methods, we have to resort to ad hoc approaches. Now, 20 years ago, something was very popular, very hot actually, was multiscale algorithms. So the idea of multiscale algorithms is to say, okay, we don't have any reliable macro scale model, but suppose we have a reliable micro scale model. So can we come up with numerical algorithms that'll model the macroscopic phenomena, but only use microscopic models? That was sort of the dream of multiscale modeling. So in order to bypass the need to come up with these ad hoc models. Now, one of the representative algorithms was called heterogeneous multiscale method, proposed by Anquist and myself. And the idea is exactly what I just described. We have this guy, this is the microscale model we assume we have, and it's reliable. And this guy, the macroscopic model, we don't have. Now, but we're interested in the modeling at this level. Now, the heterogeneous multiscale method is a methodology that allows us to do that in principle. Now, we don't need to worry about the details, but that is just one of the ideas proposed at the time in order to do what I just said. Now, the difficulty with such an idea, the why it wasn't so successful why it wasn't as successful as we expected after many years of trying. The difficulties comes as follows. There are several difficulties. One is that the microscopic model itself is not really very reliable either. So this guy oftentimes is not very reliable. For example, if you want to do crack propagation and you use molecular dynamics to model as the microscopic model, the molecular dynamics itself is often not very reliable because, especially for crack propagation when the breaking of chemical bonds is involved. So that's one problem. The second problem is that the scale that we need to do the microscale simulation is often too large. It's still out of reach. And then thirdly, perhaps most importantly, is that there's no clear scale separation. So the macro scale, the macro scale, and the micro scale, there's no clear scale separation. Now, so these are the difficulties, essential difficulties that we had earlier. But at the technical level, there's another difficulty, which is that in order to perform multi-scale algorithms, we need an effective tool to extract information out of these microscopic simulation and put that into the macro scale simulation. So we need some tool to extract data, this data estimation step. And at that time, we didn't have such an effective tool. And the difficulty with that is that we have too many degrees of freedom. For example, when you do turbulence modeling, there are just too many degrees of freedom. Many things matter at the macro scale. And as dimensionality grows, complexity grows up exponentially. So this is the curse of dimensionality. So that was the essential difficulty, other than these three difficulties that are listed here. The other difficulty is this lack of tools to do the data estimation, data processing. And this is exactly where machine learning can help. So machine learning provides a way to solve this curse of dimensionality problem. So why do I say that? Let me give you an example. This is one of the most well-known example that deep learning can do, which is classification of images. So this is the famous data set called CFA10. It's called CFA10 because all these images comes into 10 categories. So airplanes, deer, cats, dogs, etc. So given this data set, and this data set, the images are labeled into one of these 10 categories. Now, our objective is to predict if new images of the same type comes in, we need to automatically predict which category the new image is supposed to be in. So this is a classification image problem, and we can think of this as being a function approximation problem. And the target function is a function that maps each image to its category. So let's say f star is target function. So that function is defined in the space of images, and the value takes 10 values according to the category. So now this function approximation problem is very different from the kind of function approximation problem that we encountered in numerical analysis for a very long time, in the sense that the domain we're working with lives in very high dimension. So if we count the dimensionality, namely the number of degrees of freedom, you'll see that each pixel is a degree of freedom. So we have 32 by 32 pixels. In addition, these images are colored images. There's a three-dimensionality, there's dimensionality of 3 in the space of color. So altogether, the function f star is defined in a space of 3072 dimensions. So we're trying to approximate a function in a 3072 dimensional space. So this is a huge dimensionality that we never would have thought about to do in the old days. But deep learning seems to be performing such tasks very well. So why this is the case? Let me briefly discuss why deep learning can handle function approximation in such high dimension. So first, let me say why classical approximation theory doesn't work in high dimension. Well, classical approximation theory uses polynomials or piecewise polynomials, wavelets, splines, and things like that to approximate functions. Now, the kind of error estimates we have in classical approximation theory often looks like this. So the left-hand side is the error. The right-hand side, we have a product of two quantities. One quantity, the first term, is m to the minus alpha over d. So here, m is the total number of degrees of freedom in the approximation scheme, like total number of nodes in your finite element mesh. D is the dimensionality. Alpha is something associated with the approximation algorithm. And this quantity is like a quantity associated with a target function, like some norm of the target function. Now, so this kind of error estimates tells us if we want to reduce the error by a factor of 10, we need to increase m by a factor of 10 to the d over alpha. Let's take alpha to be 1. So that means we need to increase m, the total number of degrees of freedom in the approximation algorithm, by 10 to the d. If d is 3072, this is truly a huge number. So this is the problem with the classical approximation theory. And it's generic. It's generic. Now, this doesn't mean that we cannot do anything in high dimension. There's one situation in which, in a high dimensional situation, in which we have developed a very successful numerical algorithms, and this is integration. So if we want to perform this integration problem in high dimension, we approximate that integral by a sum. Here, mu is the probability distribution, say the uniform distribution, say the Lebesgue measure. So we approximate by this integral by a sum. If we do something like trapezoidal rule or Simpson's rule, it's easy to see that we also have this cursive dimensionality problem. The error goes like m to the minus alpha over d. Alpha is something that depends on whether it's trapezoidal rule or Simpson's rule. But if we do Monte Carlo, then the error, this is exact, then the error is variance over n. So error squared is variance over n. So you can see, this n is, and the m, this would be n actually. N is the number of nodes. This would be n also. So there's no 1 over d in the exponent. This means the convergence rate is independent of dimensionality. Of course, the variance could be high in high dimension. So that's why we need to do variance reduction. But in any case, we do have an algorithm whose convergence rate does not deteriorate as dimensionality grows up. As a matter of fact, in statistical physics, people perform integration of functions in millions of dimensions. And that's done fairly routinely. So routine that we forget how remarkable this fact is. What we need to do is to do the same thing, but not just for computing integral, but rather for approximating functions. And that's what machine learning does. So we can divide machine learning models abstractly into two categories. The first category are models that do suffer from cursive dimensionality. So for example, piecewise polynomial approximation, wavelets. So these kinds, or fixed basis algorithms in machine learning. So these are models that do suffer from the cursive dimensionality. There are other classes of algorithms, like neural network models, whose error behaves like this. You have some constant over m. M is the number of degrees of freedom. And then you have some other constant over square root of n. N is the number of data points. So we can show, I'm not going to go into details, we can show that there are machine learning algorithms, particularly neural network models, for which the generalization error does look like this. So this is very much like the Monte Carlo kind of bounds, but now for function approximation. As I said, we can show several neural network models do fall into this category. So these are the kind of models that can help us to overcome the curse of dimensionality problem. Now, our objective is to use these kinds of machine learning models to help us do multiscale modeling. As I mentioned before, we want to construct interpretable and truly reliable physical models, and we want to deal with situations for which there is no clear separation of scales. And I want to stress that this is a non-trivial problem. So let me say something about concurrent machine learning. So sequential machine. So this terminology is borrowed from multiscale modeling, where we talk about sequential multiscale modeling and concurrent multiscale modeling. So sequential multiscale modeling would be pre-computing. You pre-compute something and you plug it into a macro scale model. So concurrent multiscale modeling would be doing these things on the fly, but doesn't do by pre-computing, but rather do it on the fly. Now here's the same thing. In machine learning, if you first collect a label of data and then perform learning, and this is concurrent, this is sequential. So most machine learning problems in AI are sequential. Somebody collects the data, somebody else does the learning. Now, we will be dealing with concurrent learning in the sense that we need to generate data on the fly as machine learning proceeds. I'll show that in concrete examples in a minute. And in this case, we need to think about how to generate optimal data set. And the reason for doing that, I'll explain in a minute. So let me use molecular dynamics as a concrete example. So molecular dynamics, we're solving Newton's equation for a system of big N atoms. And so this is Newton's equation. Now, the difficulty is that we need a model for the potential energy function. So classically, there were two ideas. The first idea, is to use empirical potential. For example, something like the Lennard-Jones potential. So this would work for inert gas, systems of inert gas. But we're not interested in inert gas very much. We're interested in metals, semiconductors, and alloys, and stuff like that. And in those cases, it's much harder to come up with accurate and reliable. Reliability is the key. It's very difficult to come up with reliable empirical potentials, even though there are many ones that are used in popular use. But still, reliability is a problem. So this is the one approach. The other approach is to compute these forces on the fly using quantum mechanics, such as density functional theory. So the first example is the Carr-Peronello molecular dynamics. So then we will be solving, together with systems of equations of the nuclei, we will also be solving a system of equations for the electrons. And this is very expensive because each time you're doing a density functional theory calculation. So this is accurate, but reliable, but expensive. So this is the dilemma we have always been facing classically, namely the choice between reliability and efficiency. Now we have a new paradigm with machine learning. We have a new paradigm. Quantum mechanics models, like density functional theory, is only a data generator. It only helps us to generate the data. And then we use machine learning to parameterize the data and get something like some formula like these, but these are now machine learning formulas. And then we do molecular dynamics. So this will be a new paradigm. Now, in order to do this, we need to address two questions. How do we make sure that the data, where do we get the data? How do we make sure the data is good enough? And then for the machine learning model, it's not just a machine learning model, usual AI machine learning model. We need to respect physical constraints like symmetries. So how do we do that? So let me first talk about constructing the model. What kind of neural network model we need to construct in situations like this. The first requirement is that the neural network model has to be extensive. Namely, if you do a machine learning model for 1,000 atoms, and in practice you are dealing with 1,000,000 atoms, you need to be able to extend very simply, in a very simple way, the model you had for 1,000 atoms to a model for 1,000,000 atoms. So this is done by making sure that the neural network model is extensive. Now, here's one idea. This idea is proposed by Bella and Pernello. I should have the reference here, but I didn't have. Oh, maybe I missed all the references, sorry. So Bella Pernello, 2007, in a paper in Physical Review Letters, proposed this extensive model. So each one of these guys, this is the composite neural network model. Each atom, each nuclei corresponds to one subnetwork. So say you have the first atom has a little neighborhood, and these are all the atoms in the positions of the atom in that neighborhood. And then you construct some subnetwork that corresponds to this first atom. And the total energy is the sum of all the energy contributions from every atom. Now you don't need to decide which atom contributes how much energy. This is all done automatically. Now each subnetwork looks like a usual neural network. You have these coordinates of the atoms in the neighborhood, and then you construct a neural network model. So this is a sort of an extensive neural network. And the second issue is to impose symmetry. So we have translational rotational symmetry, and we also have permutational symmetry. Namely, if you relabel the atoms of same species, the total energy should be the same. So that's permutational symmetry. Now, if you don't impose these symmetries, then the accuracy would substantially deteriorate. So this is the illustration. This is the accuracy for the force. This is the accuracy for the energy. The red line shows the result after imposing symmetry, and the blue line shows the result if you don't impose symmetry. You'll see that the error differs. There's a 1 or 2 magnitude of difference in terms of the accuracy. So imposing symmetry is important. The simplest way to impose such a symmetry is to just fix a local coordinate frame. You fix, for each atom, you define a local coordinate frame by fix the origin on that atom, and then you select some, x-axis, y-axis, z-axis, and if you fix that local frame of reference, you have taken care of translational rotational symmetry. And then in the little neighborhood, in these guys, you just fix some ordering of these atoms. And by that, you also fix the permutational symmetry. If you do that, it works. That's what generates these figures. It seems to be working. The testing and training accuracy are very good. But if you do molecular dynamics, then you'll see that the total energy slowly drifts. This is the blue line, and that's not good. That's not good because that poor man's version of taking care of the symmetry creates small discontinuities. For example, when these atoms go in and out, go out and in, or in the neighborhood, or when the ordering changes a little bit, you create a small discontinuity. That small discontinuity doesn't show up when you just test in the test accuracy, but it shows up when you do molecular dynamics for a long time. So therefore, we need to have a better way to impose symmetries, and that's shown by this little lemma here. The rotational symmetry can be fixed if every quantity is, if the quantities we're having at the end depends only on the inner product, things like this. And permutational symmetry is taken care of if if the forces look like this. So here is a little lemma that that might be useful. A function, a permutational symmetric function, can always be written in such a form. We can always choose some rho or some g so that the function can be decomposed in this form. So therefore, if the neural network we come up with in the end only requires dependence on such quantities or in this form, then the rotational and permutational symmetries are automatically taken care of, and translational symmetry is easily taken care of because of if we just define the local coordinates. Okay, so this is a messy slides, but that's how that shows how we impose this idea. So the neural network we have a composition of two parts. The first part is sort of an embedding network by embedding the local coordinates into symmetric, dependence of functions like this. And the second part is a fitting network that really fits the energy. Okay. So the structure of the embedding is shown in here. So these G's are functions of this type, of the type that we just, okay, this is the better formula here. So these features are the result of the embedding, the first part. Now after the first part, all the quantities are in this form. And the second part depends only on quantities of this form, features of this form. So that ensures automatically that the symmetries are respected. And then these little g's are also modeled by neural network models. Okay, that's the first part. How do we construct a neural network model that both extensive and respect the invariants, the symmetries? The second part is how do we generate the data? Now, each data needs to be labeled, meaning computing the energy and forces on the atoms by performing a quantum mechanics calculation, like a DFT calculation. So that's the labeling process for each. Now, so that's a very expensive calculation, and in order to generate the data, we need to make sure two things. One is that we want the data set to be representative enough so that all the situation in practice that we might encounter are represented in some way in our data set. And secondly, we want to make sure that data set is as small as possible because each data point is an expensive calculation. So in order to meet that purpose, we developed something called an exploration, labeling, and training procedure. So exploration is a step that we just explore the configuration space of the system. So if you want to deal with a system of water molecules, you explore the configuration space of the water molecules. And that's done by well, there are many ways to do that. You can do some Monte Carlo steps or molecular dynamics steps, but the key thing here is that you want to explore the places where it's of practical interest and where you don't have enough data. So that's the key thing. So we need to develop some algorithms that automatically goes in places where we don't have enough data. So this is some biased molecular dynamics that we developed. And then for each configuration that we explore, we need to decide whether that configuration needs to be labeled. And that's done. Okay, let me show this figure. So the sampling step is an exploration. You explore the different configurations that might be encountered in practice. And once you have a configuration, you need to decide whether that configuration needs to be labeled. Now, a configuration needs to be labeled if we don't have enough data around that configuration. So that's the general principle. So how do we decide whether we have enough data, whether our machine learning model is accurate enough at that particular data point? Well, one way to do that is that we train an ensemble of models. We don't train just one model. We train an ensemble of models in places where we have enough data and the machine learning model is accurate. Then this ensemble of models would give very much the very similar predictions, which means the variance from the different predictions would be small. Now, in places where we don't have enough data and the machine learning model is not accurate enough, this variance will be large. So this indicator this variance serves as a good indicator whether we need to label the data point. And once we decide that the data point needs to be labeled, we do DFT calculation to label the data, and then we do the training. So this procedure is a sort of self-learning procedure, concurrent learning procedure that can be repeated indefinitely until we have satisfactory model. So this is the exploration, labeling, and training procedure. And to show you that this really makes a big difference, let's look at this example here. Here we want to train a reliable aluminum magnesium, reliable model for aluminum magnesium alloy. You'll see that the exploration procedure gives us 500 million configurations, out of which the procedure only a procedure that I just described, the exploration, labeling, and training procedure, only requires us to label less than 20,000 configurations. So this is a huge saving compared with labeling 500,000 configurations. And this is already good enough. This already gives us, very good accuracy. And for the machine learning model. And this has been tried on different systems, ranging from small molecules, big molecules, high entropy alloys, oxides, surface materials, and simple metal alloys and stuff like that. And you can see that always gives this an accuracy that's comparable to the accuracy of the underlying quantum mechanics model. Here, the quantum mechanics model is the DFT model. And if you compare like the radial distribution function, angular distribution function, some order parameters, you don't see any difference between deep potential molecular dynamics. By the way, we call this deep potential molecular dynamics, deep MD, and compare with path integral, or ab initio MD, you don't see any difference. And we have tried this. One of the success story with this is that we tried on water. Water is a quite complicated system in terms of its phase diagram, and then we were able to qualitatively reproduce the phase diagram of water, and combined with Summit, we'll put this in the Summit, and we were able to extend ab initio molecular dynamics from being able to handle 1,000 atoms to being able to handle 100 million atoms. This is actually 2 years ago. Now we can handle 10 billion atoms with ab initio accuracy. So this is the 2020 Golden Bell Prize. Now, I think the importance of this work here, it's not, well, is that it really shows you by combining machine learning with scientific computing and high performance computing, how much gain, how big a room that we have there. And we have actually developed the open source platform, the DeepMD kit, and where people can use and contribute this deep modeling open source platform. Our hope is that people in the community can contribute this, can work on this together, and construct some platform where everybody can use. We don't have to, like before, do everything from the beginning to the end by each team. We can work together, construct such a platform, and do. And this has been quite successful. There's a very active discussion group, and many has been able to help solve many problems, from battery materials, high entropy alloys, organic chemistry, biomolecular modeling, and lots of, as I said, phase diagram, water. Anyway, many problems have been solved with this. So this is my first example. Let me turn briefly to a second example. So this is we're interested in a bigger scale. In the previous example, molecular modeling, we're interested in atomistic scale. So now we are interested in a bigger scale. We want to model the fluid mechanics of polymer fluids. And again, this is a classical difficult problem. Continuum hydrodynamic models of non-Newtonian fluids looks like this. We'll talk about some solvent, solutes, polymers in the solvent, polymer solution. So here the stress, so this is the incompressibility, this is the momentum equation. The stress comes from two parts, there's a Newtonian part for the solvent, and then there is this polymer part, and it's the polymer part that's difficult. Now, classically, there's been different models like hooking, DDP models, hooking models, and then there are more complicated models like these dynamic models where C is some sort of a conformation tensor. Okay, so this is sort of a incompressible non-Newtonian fluid models. Now, the problem with these empirical models is that it's very difficult to relate these empirical closure models to molecular fidelity. If you have a different molecular structure, how is it going to different? How would be these ad hoc closure models be different? And then, other than that, this derivative here, what is called objective tensor derivative. Objective means that it has to be frame indifferent. Now this derivative here, because C is a tensor, can take different form. The requirement of objectivity does not give rise to a single choice. For example, in the literature, we have seen up-convected derivative. We have seen this covariant derivative. We have seen this co-rotational derivative. Now, which choice should be selected? We don't know. Okay, and then it's very difficult to generalize to different experimental situations. So now we're going to do this using machine learning. So our idea here is that we have some microscale model, which will be molecular dynamics of some polymer fluids, and from which we're going to generate some conformation tensor, and then these conformation tensor, we're going to develop dynamic equations, accurate dynamic equations for these conformation tensor. Now, the first issue is how do we generate these conformation tensor? So we want to generate this conformation tensor so that it best represents the configurations of the microscopic configuration. So the so-called macro correspondence. Okay. Okay. Now, of course, the underlying molecular structure could be different. Simple ideas could be like dumbbell models, could be multi-bead models. And also we want these symmetries, rotational symmetries and stuff like that to be enforced. The second idea, so once we've generated these conformation tensor, once we decided what the conformation tensors are, we need to come up with these equations, accurate approximations of these equations. And here we're going to start with the microscopic Fock-Planck equation for these molecules, for the distributions of these of the configurations. And starting from that, we can derive, at least formally, an equation for the dynamics of these tensors. Okay, so of course we don't know how these brackets. We don't know how to express this brackets. That's the closure problem that we've always encountered. But now we can use machine learning to fit a function that closely approximate this brackets. So in this way, we automatically generate a objective tensor derivative, and we automatically give accurate approximations of these dynamic equations. And these dynamic equations are interpretable in a way also. Okay, so this is the DPN squared model. It's called deep learning-based non-Newtonian dynamics, fluid dynamics. So N squared stands for non-Newtonian, and it takes this form. Okay, the details don't matter. The details involve some detailed neural network models in the spirit of what I just discussed before. But in the end, the equation looks like this. So it's very much like the classical equations, except that these tensors and these terms are based on machine learning. So let me show you some example. So the first example is simple Poisson flow of dumbbell fluids. These are dumbbell fluids, and you can see that this is the velocity, this is the stress. You can see these red lines and are the result of the MD, and the dashed lines are the result of the DPN squared model, and they're very close. But if you do hooking or Fini-P model, this is Fini-P, this is the hooking, they're very far apart. And similarly for the stress. And this is the generalized derivative, objective tensor derivative. And you can see that it's also modeled very accurately by the DPN squared model. But if you do the other guys. Okay, now here we talk about how molecular shape, different molecules, the star-shaped B, this is the Beaton springs, and this is a more complicated shape. How the microstructure affects the macro scale flow. So we have this is still in the Poisson flow framework, but at some time we reverse the direction of the Poisson flow, and then you can see that DPN squared model captures the behavior very accurately, and you can see this almost like hysteresis loop. This is not a real hysteresis loop, but you can see these loops are captured very accurately by the DPN squared model. And this is the example of a 2D Taylor vortex model, and you can see that this is a chain molecule, this is a star molecule. The molecular shape really affects the macro scale flow, the viscoelastic response in a dramatic way. And it's captured very well by this model. Okay, let me conclude. I would say the integration of machine learning with physics-based modeling opens up a whole new chapter in the way we do scientific and engineering modeling. And concurrent learning, so what do we encounter in these problems are concurrent machine learning problems, and that's required in order to generate an optimal data set, because labeling is very expensive. So generating optimal data set is very important for these procedures to be effective. And so concurrent learning, this idea of adaptively generating data sets on the fly is important. And it's important to take physics into account. So the neural network model and the dynamic equations has to respect the underlying physics. That's done by imposing the right symmetry, or deriving the macroscopic model from the underlying microscale model, and then do the closure. So, and I also want to emphasize that what do we get is our new physical models, not just algorithms. So we're not just talking about the algorithm. These guys here are potentially a new set of equations, just like Eulers equation. I remember when I was a graduate student, we were doing Eulers equation for gas dynamics with so-called real gas. And the equation of state for real gas was an issue. How to get the equation of state? Well, at the time we were getting equation state for real gas from a table generated at, I think, I don't know, I think it's Los Alamos, from experimental data. So they measured, did some experimental measurements and then fit the data by a spline and store that as a subroutine. And we were just calling that subroutine as the source of the equation state. And here it's very much the same thing. It's a little more complicated than equation state. Here we have a new set of constitutive equations. And it's also more complicated in the sense that splines are replaced by machine learning. So these formulas are machine learning formulas. But other than that, philosophically, they're very close. So I would say these are really a new set of physical models. They're interpretable and they're supposed to be reliable, and we should use them just like Eulers equations of gas dynamics. And this is what I want to say. And thank you very much for your attention.
Thank you. Thank you so much for the wonderful talk, Professor Weinan. I enjoyed it a lot.
Thank you.
There's a many questions posted by Professor Lange.
Most of them you can ignore.
Okay.
But I do have one. So they're worth going back and reading, because I did note that some of the terms you introduced, there are more very well-established terms in the machine learning literature, and I would encourage you to use them. Things like online and offline learning and active learning. You are doing the same thing. It's a good idea. It's a great idea, but there's no reason to introduce new terms when we've been calling these things for 30 plus years. But the serious question is, I've been listening over the past couple of years to people from the computational science community and the physics community who are starting to use machine learning. And there's two kinds of talks. There's one where they're using machine learning to try and speed up the simulation of a model that they already believe is correct. And the other is where they're trying to discover new laws. If I understood correctly, you didn't say this as explicitly as you might have. The first 2/3 of your talk was about the first problem, and the last part was about the second problem. Is that correct or incorrect?
Okay, first of all, about terminology. So I should have explained the difference between active learning and online learning with concurrent learning. So I think there is a big difference. For example, active learning, you have unlabeled data already given to you, and you decide which ones to label. And here in our case,
that's not true. That maybe most of the examples you've come across in literature are like that, but there are many examples of active learning where you actually select new instances that aren't even in a data set yet. They're not unlabeled instances. They just don't exist, and you have to produce them. That counts, and there have been examples of that.
Okay, so we might have to argue about this forever. So let me start about arguing about this. Okay, so I would insist there's a difference. I've talked with people about it. Okay, let's not talk about this now. With respect to the second question, in the sense you're right. I mean, the first example, all we need to do is to fit a function, the potential energy function.
Oh, I didn't say all. It's still hard. It's just I just want to be clear about what the task is.
Well, yeah, I mean, it's a hard task, but we just need to fit the function. We need to get a function. So that's very much like the first category. In the second category, the second part, it is true. It's a little bit more than fitting a function. It's getting the form of the equations and stuff like that. So
yes, I understand that. We used to call it equation discovery. Some other people call it symbolic regression. Some people call it law discovery. That's an old idea that goes back to even before the other task. So, but I have not seen it applied in this context, and I certainly am excited about your results. So thank you. I mean, I'm a big fan of stating explicitly what computational problem you're working on, and these are two different computational problems with different inputs and different outputs. And even if you're using the same underlying technology, the problems are somewhat different, and that's all I was asking for clarification about.
Okay, I'll keep that in mind and try to do a better job next time.
Thank
Well, I
you.
mean, it depends on who you're speaking to. I mean, people from a computer science background love to know what the computational abstraction is, and so that's where I'm coming from.
Okay, good.
Okay, thank you. Thank you so much. Is there any other question from the audience? I don't see any other.
Can I ask a question?
Yeah, sure.
Yeah, thank you for the nice talk. Can you go back to the slide where you show a few equations to treat the permutation symmetry?
Here?
Can you show the equations for the permutation symmetry? Yes.
Here.
This
Yeah.
one. Yeah. So I'm trying to understand these equations. So does it mean that for any interaction potential of many body system, you can always decompose it into like pairwise interaction?
No, that's not true.
Okay. So can you
okay, these
indices
IJ might be misleading. So let's forget about one index. You can see that there is always an I carried around. So that's a little misleading. So forget about the I. So it's just J.
Okay.
So here I is around because it's talking about this needs to be done for all the atoms. This is the ith atom we're talking about. So that doesn't mean it's pairwise interaction. Not at all.
Okay, thank you.
All right. Thank you. Is there any other question from audience? Can unmute yourself and ask questions. I don't think there's any other question. Professor Lange, maybe you can discuss
please,
your
if
final
anyone else can go
questions.
first. I'm happy to have you go first.
Go ahead, Professor Lange. I mean,
okay. So in the last results that you showed us, I would like to understand better how you define and constrain the space of equations that you're searching. It's clear there is a space. I just don't know what it is. And in particular, are you searching it? So is this do you specify the functional form and fit the parameters, or do you actually search a space of different functional forms? And if so, what is that space?
Okay, the starting point is the Fock-Planck equation for the underlying microscale model. And then from that Fock-Planck equation, we can formally derive a equation for the tensor C we're interested in. So that's this equation. Okay, so then in this equation, we have three brackets. We need to do a closure problem. So we need to express these brackets in terms of quantities that we already have, like C, like these C's. So that's the machine learning part. So we assume that this is a function. These guys are a function of the quantities we already have, and we find that particular function by performing machine learning.
Well, since I don't know what you mean by a closure, we're probably not going to communicate today. But if anyone else,
do you know about moment closure? Have you heard about
moment? Not a clue. No.
Oh, okay.
So that's okay. If you were going to, so for example, for this particular problem, if you were going to enumerate all possible equation forms, how many would there be?
Infinite.
So is that because they differ in parameters or because they differ in their structure?
There could be different in structure.
Then there's probably not an infinite set, but at least if you put some, so is there a bound on complexity?
So now I see you come from a computer science background.
Well, actually psychology, but yes.
Psychology, okay, that's close enough for us. Okay, now in our world, things are continuous, not discrete. So by being infinite doesn't mean much, but in this case, it's the kind of structures you could have is really just enormous. You shouldn't be searching in the space of equations. So what I'm saying here is that you should start with the underlying microscopic model, try to perform a symbolic formal calculation like this one here, and then you have these. Well, since you don't know about closure, I don't know what this. It's probably difficult to explain, but the moment closure is a very typical example that we often encounter in physical modeling, and here we're just using machine learning to help us to do the closure problem.
Okay, just for the record, there's been plenty of work on equation discovery, scientific model discovery that does search the space of symbolic structures and also does parameter estimation. So now if you're not doing that, that's fine, and I'd like to understand it better. But there are plenty of positive results where people have done that. So again, these are different paradigms. That's okay. That's why we have a lot to learn from each other. So thank you for your talk.
Mm-hmm.
Thank you. Is there any other?
Ask one more question on this slide. So this macro correspondence. So what kind of averaging is performed here, and do you find any dependence on the resolution of this? How you block average this macroscopic properties into a macroscopic properties?
Okay, so that's a very, very good question. So the average average that's performed here, in principle, that average should be performed with respect to the situation that you encounter in practice. For example, if you're doing flow, then this will be the configurations, the probability distribution for the microstructure in the flow. So here, what's done is, what's done is that we are doing equilibrium averaging. So generate some equilibrium states and then perform this kind of a quantity.
All right.
You would say Gibbs distribution or canonical ensemble.
All right. Thank you so much, Professor.
I have a related question.
Yeah, go ahead.
Oh, hi, Viren. This is Amit.
How are you?
Very nice talk. So my question is related to, again, the question that Faye asked. Do you run into time scale problem or scale problem when you do this averaging?
Say it again?
Do you run into multiscale issues when you do this averaging? Like, is the system stuck, like the same problem as we have in molecular dynamics? Is the system stuck somewhere? It's unable to explore the space that you want it to explore when you're doing this averaging?
Not here really, because there is no well, the system size is not that big, and there is no barrier crossing events associated with here. So this is a linear, almost like it's not linear response regime, it's nonlinear response, but it's in that category. You see what I'm saying? There's no there's no barrier crossing. That's also because we are doing rather simple molecules at the moment. If you do like very long chain big molecules, you would still have the issue that you just said, get stuck.
Okay.
But at the moment, no.
Okay, thank you.
Mm-hmm.
All right. Is there any other questions? Well, if there's no more question, let's thank our speaker, Professor Yi. It was a wonderful talk, and I was delighted to see your Golden Bell Prize, the examples in one of the slides, and in Lawrence Livermore National Lab there are many molecular dynamics, and they try to get that award as well. So It was nice to see that. All right. Thank you so much. With that, I think we can wrap up. I wish that with this talk, I hope there will be a lot more collaborations between, Lawrence Livermore and maybe Peking University, because you're transferring from the Princeton to Peking right now. So, yeah, let's hope that's going to happen. All right. Thank you again, Professor.
Well, thank you for the invitation.
Thank you so much. Okay.
Sure. Bye.